So now we saw that we can encode many things in the content using MIME for the email addresses, also using different alphabets. Okay, I have to admit, it's not adopted everywhere. So there are the standards, and typically the modern clients can handle it, but it's not adopted everywhere. But that was the content. Now we have to have a closer look into the transfer, forwarding infrastructure. So what does it mean? Email, basically you push the message through the network with the help of SMTP, the Simple Mail Transfer Protocol. It's simple, it's very simple, and it's a protocol, it's an old one with many RFCs, so that's the current standard to transfer emails. So it's a very simple protocol using reliable data transfer. So reliable data transfer, reliable, what does it mean? We use the classical TCP, and you see that's an old one. If you use a low port number, port 25, a well-known port with a low port number, that typically tells you, okay, this is a pretty old service in the internet because it has a low port number. So SMTP port 25 using TCP. That means with the help of SMTP, you set up a TCP connection. For example, between an MTA and another MTA, you do your TCP connection, three-way handshake. I will come back to TCP in some more detail in a later chapter. So you build up your connection bidirectional and you can start transmitting, in this case, SMTP protocol data units. So you transfer this. It's very simple. So the content delivered by SMTP, again, is simple. It's text-based. It's a client-server protocol. So the client sends something, the server receives it and gives back some OKs, etc. As we will see, it's all best effort. So SMTP is push-like. Why? Because the client initiates this setting up the connection, pushing the email over to the next server. It's not the case that the server tries to pull email from another system. So no, you push it. So you push through the messages through the network. And as always, more little or some say no security. So there's no encryption, and there is some authentication, optional authentication using a different port. But typically there's no authentication between the MTAs. So the MTAs, they trust each other and they simply accept emails if another MTA asks them, oh, you want to take over the email? Yeah, then okay. This has certain consequences, and there are some new developments, as we will see. So that's the classical SMTP. But now the question is, okay, maybe we know here SMTP, who is my next message transfer agent. Oh, how do we know this? Because typically here in your user agent, you set up the server by hand or by automated scripts or whatever. So in your user agents, your Outlook, your whatever, you have to say, okay, for me, the mail server is, for example, exchange.fu-berlin.de. Or you do this by hand by telling your user agent, well, this is the IP address of the server, etc., or the name of the server. You can even use different port number, etc. So you set this up by hand automatically. Then your user agent knows whom to contact. So that's the idea. But what happens if you then send your address? So you write, okay, I write to charliebrown@peanuts.org. Okay. Then your MTA sees, okay, this should go to peanuts.org. Who is this? And that's exactly where we then need our Amex records. We learned about this at the DNS chapter. So we have to look up in the DNS system, who is responsible, so the Amex resource records, who is responsible for peanuts.org? Because we have to know a name of the mail server. Mail server, MTA, mail relay, all the same. So we have to know this, and that means we get a name. DNS tells us the name, but okay, to be honest, this will be also translated with the help of DNS A record, you remember, to a whatever address, IP address, IP version 4 address, for example. And if I know this, then my MTA knows, okay, now I can create a socket containing an IP address. You remember, sockets consist of IP addresses and a port. SMTP, port 25. So that's my socket. This is where this is the receiver socket, the receiving side of the MTA. This is where my TCP connection ends. And then I start a TCP setup, trying to establish a connection to the SMTP server using this address and this port. As soon as I have the TCP connection up and running, then I transmit an email, as we will see. So, the steps. You write your email on sender side using your user agent. So that is basically the idea. So you write it on the client, you format it, etc. And your user agent then, well, you write the text, and your user agent then does all this formatting, producing the receiver list, etc. And then contacts the MSA, MTA mail submission agent using SMTP. This is exactly the thing you configure by hand, for example, or by automatic configuration. And then you connect it, this case with authentication. This is why we use this port 587. And then the mail is here. And then the next step follows that now this MTA checks. Remember, we have here the peanuts.org. And then this MTA has to find out who to connect. You set up this connection. Before you do this, remember DNS for the Amex records, the address, and then we know who is MTA2. Then we set up this TCP connection here. TCP is bidirectional, and we start sending a copy of the email. That's the idea. Okay, then we are on the receiver side, assuming there are no more MTAs as relays in between. On the receiver side, now we produce certain parts, the header of the email, place the email in the inbox. So there are inboxes for all different users, and we now create the header, and this is typically what is then displayed to you. And the final step would be you with your, as soon as your client is up and running, you can access the inbox and fetch your email using different protocols, as we will see. So what's going on here in between? We are now at this phase of the transfer. So what's going on in between? That's the interesting part. So how do those MTAs talk to each other? Via using the TCP connection. So simple example. So between two MTAs, remember ASCII 7 bits. So the simplest way. So typically, if you start your connection, the TCP connection is up, running, you contact the server, then the server will tell you, hey, there's a certain code, 220, beta edu service is ready. And then your friendly MTA, the first thing you do is say, hello. Why only L? Well, it's hello with one L. So hello abc.com. That means, hey, I'm abc.com. So by the way, you can also say, hello, I'm the whitehouse.gov. The other side will always say okay if the syntax is correct. You can write whatever you want. So this is whatever. So in the classical system, there's no verification. But okay, that's just an example. But you can also stay with ABC with whatever you like. So friendly enough. And the other one accepts it. Then you write, oh, I'm Bob from abc.com. You could also write here, I'm whatever, Donald from at White House, etc.gov. Or you can say I'm Olaf Scholz at the Bundesregierung, or you can say whatever you like. Again, the server checks, okay, it looks like a valid email address. I can handle this email address. If you say you're the sender, that's fine. I trust you. So it's 7-bit, it's ASCII, no verification. So this was in former times the easiest way of faking emails. Remember, 7-bit, no checking, nothing. And then it says, okay, and then you said, oh, I want to send to Alice. Okay, that's a recipient. That's important. If you write something strange here, well, mail will not be delivered. So that's a bit similar to a classical letter. A sender. Who cares about the sender on an envelope of a letter? No one. So, okay. So, Alice. So, fine. Then the sender says, okay, syntactically correct. That's a receiver. Okay, fine, great. Everything is known. The receiver is known. This is the case where the server can actually check if it can handle this receiver. Then you say data. Then the server tells you, really tells you, sending back ASCII characters, START, space MA, and so on and so on. So this is my ASCII. Nice for debugging. So you can use a terminal, very simple terminal, and do this by hand. 7-bit ASCII. Very simple. This is how the standard SMTP protocol is simply specified. And it tells you, now start writing your ASCII characters and end them with carriage return line feed, then a dot, and carriage return line feed. That means a simple dot alone on a line. So you write your text and then a simple dot. This means that's the end. That's the coding. So that's inline signaling. So now you can imagine why we cannot transfer arbitrary data over the email system. Because what happens if you have a nice picture, whatever, and this little flower in JPEG coding causes blah, 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 and why ever this causes sooner or later carriage return line feed dot carriage return line feed, because this is the coding for green grass with a red flower, whatever, in JPEG. Could be coincidence. Well, this means end of email for the MTA, because that's the way the standard works. So you see, okay, and there are some other of these effects it could have. So, but that's the idea. So you write now your text, and you end your text with carriage return line feed dot carriage return line feed. And then the other side knows, now it's over. So that's the whole text. So you never ever can have carriage return line feed dot carriage return line feed in the middle of your text, because the MTA will think after reading this, oh, that's the end. Okay, end of email. That's it. That's the specification. Okay, and then you say, okay, thanks a lot, quit. And the server is very friendly, very polite, and tells you server is closing. So this is really the sequence of messages exchanged between a client and a server, between two MTAs, the classical messages. Okay, now we see this is the command sequence. It's all transferred using TCP. Okay, so now, who creates envelopes? You write your email. You as a user and your user agent, you're not involved in this transfer stuff. That's something between the MTAs. But how does it start? Here, this example shows you what goes on in the middle between two MTAs. Well, you write your content. And the envelope is created by the MTA, MSA at the beginning. And the envelope is needed for transporting the message. So there's a difference between, transport messages and what you write as a content for the transport. We need only, in the end, we only need our, at least the receiver for all of this. So this is what you write here. So the receiver is needed. Sender, maybe, yeah. You should have it, but okay, that's not the important part. So the receiver, that's the important part here, okay? And the envelope is also sent as a series of SMTP protocol data units, and you copy this from inside from the header. So you check, okay, someone writes, I want to write an email to alice@beta.edu, and then the first MTA takes this out, writes it on the envelope. So we are happy. We will also see examples that inside our content may be extended while the email travels through the systems. So we have data inside in our content, and the header there can grow. And for example, we will see how certain information about the path of the email is stored in the header. So there are certain functions, but the most important part is that the MTAs, they handle this transfer and they take care that this important information is here on the envelope and you don't need all the details. And we'll see this in the example later. What's quite important is no one checks if the information is correct. So no checks, nothing. I mentioned this several times just to tell you, okay, email is nothing you can trust for 100%. You can change these things, so no checks. And also, you don't know if the sending MTA is really authorized to send mails on behalf of the sender address. And that's one of the problems, that every MTA, if the operator allows, can send an email in your name. Why not? So there are spammers, they take your name, your email address, and simply claim that this is the sender of the email. Okay. And also, the data in the email header, so the header that's inside your envelope, does not need to comply with the data on the envelope. So that's two different things. The envelope is needed for transferring the message inside the system. The header is then used by the user agent on the receiving side, for example, to see, oh, that is the subject, that is where it's from, etc. So just a simple example for spoofing emails. Well, connect yourself using Telnet. Very old thing, to port 25, if the mail server allows this. And then, in this example, it works. And you simply say, okay, the mail is from the president at White House. Why not? And please send it to my colleague. Syntactically, everything fine. This is why it says okay and accepted. So I know how to deliver it to this colleague. And then you enter a message. And here you can enter whatever you like. Whatever. So that's my header. So my header of the email is now you can write whatever. So don't get confused. We need something for transfer. This is for the transfer for the envelope. And then we have the message. message, and it could, you can write whatever you like, you can invite yourself, you can do whatever you like, and then you have your blank line, you have your text, you have your, this is my single dot carriage return line feed, and this is my single dot. Then the MTA knows everything is over, so you played basically MTA. So you played an MTA, connecting another MTA and talking to this MTA. And this works. So, in the end, there is no security by design. So, email is a very simple system, and quite often in the internet, let's try something. It works. Okay, we have a nice service. And later on, we start thinking of security. There are pros and cons for this. Thinking of everything, of all the problems, will lead to a never-ending story. Starting at least gives you a system you can then improve, but you have no security by design. A simple example what you can do to fight spam is called greylisting. What does it mean? So greylisting is quite often used. It's very, very simple. The big advantage, it runs on the MTA of the receiver. So you can implement this, and this is used by many mail providers. So it says, okay, the MTA reads from the envelope 3 things. One is the IP address. So that's the first thing of the sending MTA. Because we have a TCP connection, we know exactly where the mail comes from. So, okay, we know the sending MTA. Well, then we check the envelope and we check second, mail from. Okay, where does it come from? And the third thing is, so recipient. So we have this triple. And now, if we see this triple the first time, we reject the email and send back an error code. Okay, that sounds strange. It could be a valid email. Yes, but still we say, no, sorry, we don't accept. The idea behind this is that normal MTAs, non-spamming MTAs, will try again after a minute, after 10 minutes, after whatever. Try again to deliver the email. And the assumption is spammers don't do this. Okay, we can discuss this, but okay, we assume spammers don't do this. This means that the second trial will be okay. If you see it a second time, you receive the email and forward it. Fine. So the idea is that spammers won't do this, but normal emails will be repeated. Remember, I told you it's a store and forward system. So you repeat the email and then it will go through. The disadvantage is that you delay all emails. So you delay all emails if seen the first time, this combination. And maybe sometimes you experience this. You send an email and you think, why doesn't this email go through? Then you send the email a second time and it immediately goes through, and the first email also arrives. And you think, oh, this is strange. So, but hey, there's no guarantee with emails. So this could be one of the reasons. Additionally, you do something called white and blacklisting. So this is greylisting, something in between. Whitelisting, that means you can tell the system, I definitely accept emails from this and that server. So you can say, okay, I trust my company server, for example. I will not do greylisting if it comes from an MTA from my company. Then those mails go through immediately. And you can do blacklisting, for example, I will never trust this and that MTA. So you could, for example, blacklist all MTAs on this planet that spread spam. Okay, sounds good. So we blacklist all MTAs. As soon as someone experiences, oh, there's a lot of spam coming from an MTA, we block them. Yeah, some providers tried this, and then the customers complained because you will have problems receiving all the mails. So that is a problem. So this will simply exclude some countries and some big operators from international mail exchange. So that's a problem with blacklisting. What are some additional techniques? We cannot go into all the details because this would make you maybe to email professionals, but we have so many topics to cover. Just some pointers to 3 more systems. Quite often used in combination, so Greylisting plus, for example, sender policy framework, domain keys identified, mail and domain-based methods, authentication, reporting, and conformance. Those systems, what do they have in common? They typically heavily use DNS, and some of them use some cryptographic hashes to check if this is really a valid MTA. Some others use the DNS, reverse lookup, etc. if this is a valid MTA, etc. To check if you can trust the sender. So have a closer look into this if you're interested. Greylisting, just to give you an example. Yes, we can try this. So just to show you how this works, we do the example. Colleague tries to send email to himself, and the system will say, "You're not yet authorized. That's my first time. Try later." Okay, now depending on the setting, no, you're still not authorized. Try later, and then you try a 3rd time, accepted, and then you send your spam. So, yes, yeah. Greylisting, that's just one way of doing. It is partially successful unless you try several times. So one way to go around greylisting is trying it several times. Okay, so we're talking about transfer, and what do most people see? In the end, just to say who has your email, huge MTAs, etc. For many people, it's Google. Google having 1.5 billion customers, something like this. So if you look at that, so Google is the green part, and you can check the percentage of domains in each set. So depending on what you look at, so it's something like about 1/3 of all email is with Google here, the green one, followed by 10 to 12%. It's Microsoft, etc., etc., etc. And also, if you look at different countries, it's interesting to see that for most countries, Google is the dominant provider, and you also have Microsoft. So depending on the country. So for example, in Canada, it's more Microsoft than Google, etc. So in Germany, it's basically the same. And then you have countries. If you look at countries, China, for example, there's no Google. And also Russia, etc. They have other providers. So they have Yandex. So it's quite interesting to see who has your mails. By the way, typically mails are clear text and gives those companies perfect insight into everything you're interested in. All your likes and dislikes and what you think, etc., etc. So think about this. Coming back to a bit of technology, why is email spoofing that simple? Go back to the architecture, how this was designed, and why is it that easy? What is the idea then of greylisting, a way of preventing this spoofing? And then please do have a look at SPF, at all the different other architectures, frameworks. So, and then think of, if you just pick one, SPF, for example, and then why, again, coming back to DNS, why is it so important to protect this phone book, our DNS? Why is it even more important if you look at the frameworks? And now we have the frameworks with greylisting, it's fantastic, so why do we still receive spam? And maybe in addition, you know that we can also rate emails, so spam filters, doing some rankings and ratings, etc. And we know that typically we can sort out with the help of junk mail filters, spam filters, etc. most of the spam mails. Still, there's still a certain percentage. What type of spam is basically impossible to filter out? Well, we can discuss this.